This lecture series introduces the use of bipolar junction transistors in single transistor analog amplifiers. This material assumes that you've had some introductory or you have some introduction to bipolar junction transistors. Not much, but basic, the terminal names, the symbol, the fact that there's an NPN and a PNP transistor, basic operating mode, specifically as to how they relate to the equivalent to the MOSFET transistors. So there's a cutoff, there's a saturation, there's an active region. We will go over briefly the large signal and the small signal models that we'll be using in our in the lecture here. But it would be good to have at least a brief introduction to bipolar junction transistors before viewing these lessons. The goal of this set of lessons is going to be to move ultimately to the three standard amplifier, single transistor amplifier topologies, and those are the common emitter, the common base, and the common collector amplifier topologies. And we're going to do it in 4 steps. We're going to look at some large signal problems. We're going to look at some DC biasing problems where you're going to bias up an amplifier stage to some initial DC operating point. Then we'll look at the small signal equivalent circuit of an amplifier circuit, and finally then we'll look at the 3 amplifier topologies, and we'll be looking at things like the open circuit voltage gain or short circuit current gain, input resistance, output resistance, and we will be doing this by way of examples. So all of this material will be introduced by way of examples, with the exception that I have a first slide here that provides the theory that we'll be using to work our way through this material. So we have some assumptions or guidelines that I will go over before we start working examples, and of course these examples will be spread out over multiple video lessons. So A, we're going to consider circuits in the active region and avoid cutoff and saturation. So if you recall that for a transistor, if we have a collector current versus a collector T emitter voltage, this would be for an NPN transistor, we will have a family of curves that look like this. These are for all different base currents, where this will be higher base currents as you move up. And so we are going to work in the active region over here. Okay, and that assumes that the transistor behaves as a current source or current sink. We're not going to be in cutoff, which is down here, and we're not going to be in saturation, which is to the left there. So we're looking at the active region. In the active region, the model that we will use for an NPN transistor will be a base emitter junction diode and then a controlled current source from collector to emitter. We can express the current from collector to emitter in 2 ways. We can say that it is beta times the base current, where beta is the forward gain. Typically we'll use 100 as a typical example. We can also express it as some scaling current IS times the exponential e to the VBE, the base emitter voltage, divided by the thermal voltage. I should write here that the base current is going to be 1 over beta, the collector current. This is going to be true for when the device is in saturation, or not, no, when it's not in saturation, sorry, when it's in the active region. And so to stay in the active region, we need to make sure that the collector to emitter voltage is greater than the VCE sat, which typically we'll use numbers of 0.1 to 0.2 volts for saturation. Also, we should say that IB is going to be greater than 0. Okay, so in order for it to be in active region, we need to have some base current flowing. And then on the right here we have the PNP equivalent, and it works just the same way, but there you'll notice that the currents are in the opposite direction now. So IB and IC are pointing from emitter to base and emitter to collector, which is the flip from reversed from the NPN, and instead of noting the VBE voltage, we note the VEB voltage. But beyond that, we have really the same relationships. We'd have the base current is 1 over the beta times the collector current, and we'd have the collector current being equal to beta times the base current, and also the scaling current times the exponential VEB, now not BE, but VEB over the thermal voltage. Of course, VEB will be positive here. And to stay in the active region, we need the emitter collector voltage, not collector emitter, but emitter collector voltage to be greater than the VEC sat, which again we'll use around 0.1 to 0.2 volts. So that's going to be our model that we use for large signal problems. Now for most biasing problems over here in assumption B, we have that we'll assume a constant VBE model. So in other words, we'll not use the exponential relationship where we would say that the collector current is some scaling current IS times the exponential VBE over thermal voltage. Instead, we'll simply say that the collector current is beta times the base current, and we will replace the diode. We'll replace the diode with just a voltage drop. So this would be our model for an NPN, and we'll use typically 0.7 volts for the base emitter voltage, and we will write that the collector current is going to be equal to beta times IB, and we'll just draw IB, we'll label it here. Now clearly if we were applying a voltage source directly across the base emitter voltage, then this model wouldn't work, because this model forces base emitter to be 0.7, and if you have an external voltage source applied directly across VBE, you're going to have a conflict. And so in that case, we would have to use the full large signal model with the exponential, which would then describe the collector current as being proportional to the e to the VBE voltage over the thermal voltage. For most of our biasing problems, when we're trying to bias up an amplifier prior to deriving its small signal equivalent circuit, we will use this simplified model, the constant VBE model. It is accurate enough in many cases, most cases, and it greatly simplifies things because we don't have to deal with an exponent or an exponential nonlinear function. Okay, lastly, we have the small signal model for our transistor in the active region. Again, I have the NPN and the PNP, and I also have provided it in two forms. There's a hybrid pi model, and then there's a T model. They're equivalent, but they come in handy. They each come in handy to a differing degree based on the circuit, the amplifier circuit that you are trying to analyze. So I have both of them here. Essentially what we've done is that the diode junction between emitter and between base and emitter has been replaced with a linearized resistor. So this is just the incremental resistance of the diode. It's the slope of the IB versus VBE curve, and it is expressed down below here as the thermal voltage divided by the base current. We can also write it as beta times or beta over GM. Now GM is the transconductance of the transistor, and it relates the collector current linearly to the base emitter voltage, and it is equal to the DC collector current divided by the thermal voltage. For a PNP transistor, it looks much the same. The only difference is that our GM current orientation is reversed, and the controlling voltage is VEB instead of VBE. Over in the T model, what we've done is we have related the collector current not to the base current, but we've related it to the emitter current. And I should write here that alpha is defined as beta over beta plus 1. That ratio comes up often enough in these circuits that that another symbol is defined for that ratio. It's alpha. And for betas that are substantially large, so let's say for a beta of 100, alpha approaches 1. So for a beta of 100, we'd have 100 over 101, which is, you know, 0.99 or so. So in the T model, what we have is that the collector current is alpha times the emitter current, and then the emitter current is actually determined by the VBE voltage. So it's a resistance RE, E for emitter, and the current that flows out the emitter is going to be equal to the base emitter voltage divided by RE. Okay, so, but if you think of it, let's say that let's say RE was 10 ohms. If VBE was 10 millivolts, then we would have 1 milliamp flowing out of the emitter, right? We'd have 1 milliamp flowing out of the emitter, and let's assume that beta was 100, and so alpha would be 0.99. So of the 1 milliamps that's flowing out of the emitter, we would have 0.99 milliamps coming from the collector, and that would leave 0.01 milliamps flowing from the base. So in other words, 10 microamps. So now 10 microamps controls 1 milliamp, nearly 1 milliamp of current. So that's our T model. The model for the PNP is, again, almost identical. The current polarities are reversed, including that of the controlled source. So with that, I think I will stop here, and we'll break this into a second video where we'll start working some problems using this content.